ourselves using a spherical coordinate system. So we plot electric field as a function of theta and phi. So we keep R constant. R means distance from the source, that is distance from the antenna. We see a far off, at a far off point, we find the expression, we find the pattern for it. Okay, we keep R constant and vary theta and phi. So the parameter may be either electric field or magnetic field or power density or polarization. So many parameters are can be plotted as a function of theta and phi. So the main this thing is the electric field pattern and the power pattern. Okay, electric field pattern, we keep R constant. R is a far off distance from the antenna. R is the distance from the antenna, which is point is very far away from the antenna. So we are interested in the R fields. So we vary theta and phi. Theta is to complete one complete sphere. So what is the limits we have to vary with theta and phi? Theta should vary from 0 to pi and phi should vary from 0 to 2 pi. Do you understand now? Is it clear? Hello? Hello?
Yes, sir.
Yes, sir.
So here we say, so the plotting is done in spherical coordinate system. That is convenient. So antenna studies also is done using spherical coordinate system. We derive the derivations or whatever this thing computations we use using spherical coordinate system. So here you can see the radiation pattern. Now I told you what is radiation pattern is plot of electric field as a function of theta and phi. R is kept constant. R is very large far away distance from the antenna. So here you can see the main lobe, one of the main lobe here you can see, and these are the side lobes. That is, in this direction the radiation is maximum. Most of the energy is concentrated in this direction. Okay, these are the side lobes. Okay. So here you see the spherical coordinate system. So an elemental area is shown in the spherical coordinate system. Okay. So elemental area, you keep R constant, theta and phi. Theta is incremental d theta in the theta direction and incremental d phi in the phi direction. So the elemental area is R d theta into R sin theta d phi. You know this, you have studied this in EMW. So the elemental area is R, you can see here, R square sin theta d phi. Okay. So do you get it now? Is it understood? Can I go to the next slide? Hello?
Sir, when we are finding the electric field,
Yeah.
sir, why we are not, sir, are we interested in both the far field as well as near field?
See, near field is of not much of importance to us. There are so many reasons for it. And the main focus, we are using antenna, we are trying to increase the distance between the transmitting and receiving antenna. It's better to have a larger spacing because we can save on the distance. You don't have to use repeaters. Okay. The farther the distance, so far field is of more importance to us in an antenna.
But sir, in the near field, I think minor lobes come under the near field, right?
We will study that later. But now take it as this is the far field. Yeah, our interest is only in the far field.
Okay.
Now take it as our interest is only in the far field region, that is far off distance from the antenna, transmitting antenna.
Thank you, sir.
Okay. So all our most of our discussion will be focused on the far field region. Okay. So this is a pattern in the far field region, that means a far away point from the antenna. So here a spherical coordinate system is being shown. Elemental area is being shown here. So the direction of the area is in the R direction. So R cap, R square, sin theta, d theta, d phi. So that is dA, elemental area. So if you want to cover complete sphere, what we have to do? We have to vary theta from 0 to pi and phi from 0 to 2 pi. You have studied this in EMW. You know this. Okay. So that will completely cover the antenna. A sphere, when you vary the theta limits from 0 to pi and phi to 0 to 2 pi, it will completely cover the antenna. Okay. So I'll go to the next slide. So you can see here r square sine theta d theta d phi. So if you just do the integration, full limits, if you apply the full limit, 0 is theta is equal to 0 to pi and phi is equal to 2 pi, you get the area of the sphere 4 pi r square. That is shown here. So radiation pattern. Okay. As per this slide, it is a mathematical or a graphical representation of the radiation properties of an antenna, such as amplitude, phase, polarization, etc., as a function of angular space, coordinates theta and phi. See, although r is also a coordinate, we don't consider it because at a far off distance, the pattern is independent of r. That means even if you vary the r, the pattern will shape of the pattern will remain same. So at a far off distance, the pattern remains independent of r. So you vary only theta and phi. Okay. So radiation pattern is a mathematical or graphical representation of radiation properties of an antenna, such as amplitude. Now, what could be the amplitude? Amplitude could be electric field amplitude or the magnetic field amplitude. Okay. Phase is electric field is a vector. Electric field or magnetic field is a vector. It has a magnitude and a phase. If you plot the amplitude, then you have amplitude pattern. If you plot the phase as an angle of theta and phi, you get the phase pattern. Then he has discussed about polarization also. Polarization, see, there are different components in electric field. There is R component, theta component, phi component. So polarization refers to the a particular this thing. The amplitude is you have theta square, E R square, E phi square. That is the total square root of that. That is the amplitude. But polarization refers to a particular component, ER component or E theta component or E phi component. Okay. So in general, I have a very beautiful notes. Okay, I will take PDF of that and send it to you. But meantime, I will just explain using the PPT. So it will be difficult for me to explain from the place the notes, present the notes, because it is not presentable as like PPT. So it can be shared as a PDF file. Okay. So are you able to hear me? Hello?
Yes, sir. Yes, sir.
Is it fine? If you have any problem, before going to the next slide, I will just ask you. Okay. So in general, what is radiation pattern? A radiation pattern is a mathematical function or a graphical representation of the radiation properties of an antenna, such as a function of space coordinates. Radiation properties include power flux density, radiation intensity, field strength, polarization. So we can use two or three dimensional pattern. So why two or three dimensional pattern? For example, see if you vary theta and phi both, and theta and phi are independent variable, the amplitude is a dependent variable. So theta and phi both you vary, and you plot amplitude, then you get a three-dimensional plot. If you plot amplitude as a function of theta alone, or if you plot amplitude as a function of phi alone, you get the two-dimensional plot pattern. Do you get it? Plot, two-dimensional plot. Hello.
Yes, sir.
So so basically amplitude. So there are different characteristics, different properties include power flux density, radiation intensity, field strength, polarization. So all this I have not discussed. Now I am just focusing on amplitude. So I am plotting amplitude as a function of theta and phi. So if you vary both theta and phi as independent variable and plot amplitude, then you get a three-dimensional plot. But if you You usually three-dimensional plot is very difficult. So if you two-dimensional plot, what we do is we keep phi constant and vary theta from 0 to pi and plot the amplitude versus theta with phi constant. That is one plane. In the other plane, we keep theta constant and vary phi from 0 to 2 pi. And this amplitude versus phi. So R is not a consideration because R at far off distances the pattern is independent. The shape of the pattern is independent of R. So is that very clear? Hello.
Yes, sir.
Yes.
Okay. Now let us try to draw a pattern. Okay. Now I'll tell you how to draw a pattern. So let me just, for example, so suppose it is given like that. E electric field is given as B naught sin theta. B naught sin theta. So how will you draw this pattern? B naught sin theta. So first, I said we are using spherical coordinate system. So let us draw the z-axis. Let us say this is the z-axis. So you know what is theta? Theta is the, if you take a point, if you take this point, theta is this angle, basically this angle. This is theta. Theta varies from 0 to 2 pi like this, 0 to 2 pi. Are you getting it? Hello?
Yes, sir.
Okay. Now, if you plot sin theta, now this expression for electric field is given as B naught sin theta. So if you plot sin theta, how will it look like? See, this is the z-axis. So I'll just draw the pattern. See, sin theta will be like this. Do you get it? Sin theta. Have you understood? At theta is equal to 0, sin theta is 0. So this is the origin. Say, let us say this is the origin. I'll just draw a line here. This is the origin. At theta is equal to 0, sin theta is 0. At theta is equal to 90 degrees, it is maximum. Okay? And 180 degrees again it is 0. So this is pattern for sin theta. Do you get it?
Yes, sir.
Okay. Now, how do you suppose now let us say pattern is say E is equal to B naught cos theta. E is equal to B naught cos theta. So how is the pattern? So this amplitude basically here is B naught. Can you see this? I'll just see this amplitude is B naught. This is 0 here, 0. This is B naught, again 0. Have you understood? So these are angles. These are the different angles. Like this. So B naught cos theta. So any feedback? Are you getting it or not? Is it fine? Hello?
Yes, sir.
Yes, sir.
Yes. So B naught cos theta. Let us plot B naught cos theta. Let us see how it will look like. So here, this is the z-axis. Okay. So this is the origin. Let us say this is the origin. Center z is equal to 0. Okay. Now if you plot B naught cos theta, it will look like this. Like this. You get it? So this should be properly like this. Okay. Do you get it? B naught cos theta. It is maximum at 0. Maximum at 0 and 90 degrees. It is 0. Do you get it?
Yes, sir.
Okay. So this is B naught cos theta. So sometimes what happens is you plot the normalized pattern. Normalized pattern, how do you get? How do you get the normalized pattern? For example, E is nothing but En. It is normalized pattern is called En. Normalized En. How do you get En? En is equal to E divided by E max. E divided by E max. E divided by E max. Okay. So what is En in case of the first equation? E is equal to B naught sin theta. En is sin theta. Okay. Similarly, for the second equation, En is cos theta. So because maximum value is B naught sin theta divided by B naught. So you get sin theta here, you get cos theta here. So that is called the normalized pattern. Okay. Normalized pattern has E max equal to 1. Normalized pattern has maximum value equal to 1. Okay. Now, what is the direction of maximum radiation in the first direction of maximum radiation? In the first plot, what is the direction of maximum radiation? When do you get maximum radiation? When the amplitude is maximum. When the amplitude is maximum, you get maximum radiation. Okay. So, what is the direction of maximum radiation here in the first plot? In the first plot, the direction of maximum radiation is 90 degrees because sine 90 is 1, that is maximum. Sine 90 is maximum. So you get maximum at 90 degrees. Here, you get maximum at 0 degrees in the second plot. You get maximum at 0 degrees. Cos theta is maximum at 0 degrees. It is so. What is the direction of null in the first pattern? It is 0 degrees. Direction of null and 180 degrees. Direction of null in the first pattern is 0 degrees and 180 degrees. Direction of null in the second pattern is 90 degrees. Direction of null in the second pattern is 90 degrees. So are you able to get this? Direction of maxima, direction of null. What is how to draw a pattern? So you have to keep on assigning values to theta to draw the pattern. You have to keep on assigning values to theta and draw the pattern. Okay. And if you in ML you can draw the sometimes the pattern is dependent on only one angle, that is theta or phi. Sometimes pattern is dependent on both angles, theta and phi. Suppose we have, let us say, E is equal to, suppose it's given like this, B naught cos theta Sin phi. If suppose electric field is given as B naught cos theta sin phi. Now, how do we draw the pattern? In this case, we have to draw the pattern in two planes. One, you have to keep phi constant. For example, phi constant, phi is equal to, say, phi is equal to 90 degrees. Okay. So sin phi is 1. So in that case, to draw the pattern in the phi is equal to constant plane, phi is equal to constant plane, and that pattern will be E is equal to B naught cos theta. So if you want to find in the other plane, phi is equal to constant plane is what actually? Phi is equal to constant plane is a vertical plane. Can you understand that? Phi is equal to constant is a vertical plane.
Yes.
That is very important. Do you understand? Phi is equal to constant plane is a vertical plane. Theta varies from 0 to pi. So, okay.
Yes, sir.
Okay, and another plane is so we can't draw a three-dimensional pattern. So we have to go for you have to take the cross section. That means one keep pi constant and vary theta from 0 to pi. Okay, and in another plane we treat theta constant and vary phi from 0 to 2 pi. So theta is equal to constant is what? Say, for example, theta is equal to say theta is equal to some say 45 degrees or something. Theta is equal to you get cos theta something 1 by root 2 of B naught. Okay, and sin phi. So that is the horizontal plane. Do you get it? Theta is equal to constant plane is a horizontal plane. So the pattern becomes that time it becomes E is equal to B naught by root 2 sin phi. So you plot sin phi. Are you getting it? Hello?
Sir, isn't it a conical structure?
Yeah, I'm not discussing about that now. But if you, I'm just saying how to plot it in different planes. Okay. What I'm not going to the pattern of that. I'm not discussing the three-dimensional plot of that. Just if it is given to you and if you're asked to plot, you have to keep phi constant in one plane and in for one plane, and for another plane you have to keep theta constant. So you treat the other variable term as 1. Keep it as cos theta or sin theta. Cos theta as 1 or sin phi as 1 when you plot it. So that's how you plot. Okay. Now I will tell you if there is a power pattern. Now let us see. E is equal to B naught sin squared theta. Let us take that. E is equal to B naught sin squared theta. How the pattern will look like? E is equal to B naught sin. Hello, yeah. Hello. There is some disturbance. Hello, are you getting me?
Yes, sir.
Now let us say electric field is given as B naught sin squared theta. So what will be the plot? What will be the plot? So sin squared theta is sin theta into sin theta. Okay. So this will be more directional. That means it will be like this. More directional. Do you get it? Sin theta into sin theta when you multiply, it will be more directional. Okay. Now, what is the direction of maximum radiation here? Sin squared theta. Same 90 degrees. Direction of maximum radiation 90 degrees. Direction of null is 0 degrees and 180 degrees. Direction of null means 0 amplitude. Direction of null means 0 amplitude. 0 degrees and 180 degrees. Okay. Sin square theta is like, now how do we find half, okay, you know, sin theta is equal to B naught sin theta. How will you find half power point? How do you find, suppose E is equal to E naught B naught sin theta. How will you find the half power point? Sin theta. Half power point means what? Half the maximum radiation. Direction of half the maximum radiation. So maximum radiation is in 90 degrees. Sin theta. Okay. Half power point would be somewhere here. So how do we get that point? Okay. So that is called theta HP. Theta half power. Theta HP. So if you are getting confused, please let me know. I will clarify it out. So theta HP, if direction of half the maximum radiation is half power point. So how do you get that? So if you do this calculation, D naught sin theta is equal to sin theta HP half power. I call it as theta HP will be equal to what? What will be B naught sin theta HP? What will be B naught at half power point? I said it is the point where you get half the maximum power. So what will be B naught sin theta HP equal to? Hello? Not able to hear?
Half B naught, sir.
So
It is
1 by
0.707. It's 0.707 B naught. Why 0.707? Because power is half. Electric field will be, what is power? Square of the electric field. So 0.707 is 1 by root 2. So 1 by root 2 into 1 by root 2 will be half power. So have you got it? How to get the half power point?
Yes,
Sir,
sir.
can you re-explain one more time, sir?
Yeah, see, for example, E is given to be B naught sin theta. And what we are expected to find the direction of half power point, find the direction of half power. That means half the maximum power. So maximum is where? At 90 degrees. At 90 degrees. Okay. Half maximum is at 90 degrees. Half the power is where you get half the maximum value. Maximum value is B naught. Half the maximum power. So if power has to be half, the voltage should be, electric field should be 0.707. Right, no?
Yes, sir.
Are you-
Yes, sir.
Okay, so B naught sin theta HP is equal to B naught sin theta HP is equal to 0.707 of B naught. So this is the angle theta HP. So now what is the half power beamwidth for this? Half power beamwidth means on the either side of the main maximum. What is the half power point? For example, either side of the maximum radiation. What is the half power point? So this is 30 degree. This is how much? 0.707 is 45 degrees, right?
5 degrees.
45 degrees. Okay. So similarly here, 90 plus how much? 45 degrees. You get other half power point. Do you agree?
Yes, sir.
So what is the half power beamwidth? 90 minus 45 into 2. Do you get it? 90. This is the direction of maximum radiation. For sin theta pattern, 90 minus 45. So that is the into 2. So 90 degrees. So half power beam width is for sin theta is 90 degrees. Do you get it?
Yes, sir.
For cos theta also same thing. If you want to draw the half power beam width, it's called HPBW, half power beam width. It is 90 degrees direction of maximum minus this angle. So you are interested in this. See, you are interested in this angle. You draw the other half power point is here, for example. So this angle basically, this angle. So that is 90 minus. See, my diagram is not very clear, but can you make out? Can you understand? Hello?
So I
Yes,
didn't
sir.
understand the last thing you said.
See, I am interested. First of all, I am interested in theta half power point. So you.
Sir, your voice is breaking a lot.
Sin theta has half power points at theta is equal to 45 degrees and theta is equal to 135 degrees. Do you understand this? Hello?
So your voice is breaking in between.
We are not able to understand. So the slides is also lagging. So your voice is also breaking. So is there some better connection there, internet connection?
Connection, I have no control on that, no. Connection, I have no control. So let us try to make maximum. I'll try to explain once again. See, theta HP, one of the points is 45 degrees. Understood? No? Sin theta is there. One of the points, theta HP, half power points. What are the half power points? One is 45 degrees. I understood that.
Yes, sir.
Okay. See, this is the 45 degree angle. 45 degree. So this pattern is like a circle, no? So there is on the other side also there is half power point. So what is that? 135 degrees. 135 degrees, this angle. Do you get it? 45 and 135.
Sir.
So in between the half power point, we have half power beam width. Half power beam width. How do we get that? 135 minus 45, that's the half power beam width, or 90 minus 45 to 2. Half power beam width. 90 minus 45 into 2. Because it is symmetric. Why into 2? Because it is symmetric. Pattern will be symmetric always. Okay. Do you get it? Hello?
Sir, is it the angle between two consecutive half power angles?
Yes, yes. Same thing. One at 45 degrees, you have one half power angle, and the 135 degrees, you have half. In between that, on either side of the maxima, half power. So that is the half power beam width. Half power points on either side of the maxima. That is the half power beam width. This is the half power beam width. So this is the direction of maxima. 90 degrees is the direction. 90 minus 45 to 2.
Okay, sir.
Got it? So similarly for cos theta, tell me what is the half power point? For cos theta, this is the cos theta pattern. Cos theta. What is the direction of maxima is 0 degrees. Direction of maxima is 0 degrees. So what is the direction of half power point?
45 degrees.
45 degrees. Same. Now how do you find the theta HP? So here 45 degrees, 45 degrees. So it is not 90 minus in this case. 45 degrees into 2. It is not 90 minus because it is this angle is 0. You don't have to 90 minus, you don't have to. Okay. 45 into 2, 90 degrees. Do you get it?
Yes, sir.
See, these are the.
Yes, sir.
This is one. This is one. Like this. So in bit, this is bit half hour beam width. Half hour beam width is this. This is half hour angle theta HP. This is HPBW. This is theta HP. This angle is theta HP. This angle is theta. This is half hour beam width. 2 into this thing. Theta HP is half hour beam width. In this, you don't have to 90 minus. You don't have to do because this angle itself is 0. Here this angle was 90. So that's why you have to do 90 minus this angle into 2. Have you understood? Hello?
Yes, sir. Yes, sir.
Okay. So you have understood how to find the direction of maxima, how to find the direction of null, how to find the theta HP, that is the direction of half hour point, and how to find the half hour beam width. All these things you have understood, right? Till now?
Yes, sir.
Tell me if I can improve in some way, because the limitation of extent of I can go, because this is not that convenient what I draw here. Okay, so we have discussed the amplitude pattern. So we have discussed the normalized amplitude pattern. Okay. Now you have understood this sin theta HP. So here also, so if you want to, can you draw this B naught sin square theta? Can you find out what is the direction of maxima? What is the direction of null? What is the direction of what is theta HP and HPBW? Can you find out for sin square theta? How do you find out? Direction of maxima is same, 90 degrees. Okay. Direction of null is also same, 0 degrees. Theta HP, how will you find out? Sin square theta is equal to
0.707.
Yes, sin square theta HP is equal to 0.707. That's how you have to find out. And then after finding theta HP, 90 degrees minus theta HP into 2. That will be HPVW. Okay? For sin square theta HP pattern. Is it clear? For cos square theta, you have cos square theta HP is equal to 0.707. So that's how you have to plot. Okay. Is it clear?
Yes, sir.
Oh, okay. I'll erase this. Anything to note here? If you want to note something, you can note down. Otherwise, I'll erase it. Can I erase it? So, what is the direction of null? Null is basically a direction where the amplitude is 0. And what is the direction of the maximum is where you get maximum amplitude. Okay. So, I'll erase this. So can I erase it now?
Yes, sir.
Okay, now let us say there is a pattern like this. E is equal to sin theta cos theta. Suppose there is a pattern like this. So how to draw this pattern? So naturally you have to keep on assigning values from theta is equal to 0 to pi and find out the value of E at all different angles, different values of theta. So you know sin theta pattern. Sin theta pattern is like this. Sin theta pattern is like this. And cos theta pattern, you know, it is like this. right? No.
Yes, sir.
So E is equal to sin theta into cos theta. So basically, how many nulls it will have? The main pattern, the final pattern. It will have nulls at 0, 90 degrees, 180 degrees, right? No, because this has nulls at 0 and 180 degrees. This has null at 80 or 90 degrees. So pattern could be something like this. Sin theta cos theta. It should be symmetric. So have you got it? How to draw the pattern?
Excuse me, sir.
Mm.
Sir, we are varying theta from 0 to 180 degree, right?
Yes, yes.
So, sir, shouldn't we get the graph only on one side of the lobe?
No, see theta. It is, but it is same as on the other side. You see theta. And this is the z-axis. Theta is not in one vertical plane. See, when it's also theta. No? This angle is also theta. Both are theta. This also theta. This also this angle. So this same thing. It's a replica, mirror image of that.
Sir, we are not following any here positive negative convention.
No, we are not following positive negative convention.
Okay, sir.
Okay, all of you have got so how to draw the pattern. Okay, so if it is both varying in sin and cos, we have to keep one constant and vary the other and plot it. Okay, we'll continue. So if a power pattern is given, suppose U is equal to, if B naught, so let us say this, I represent it as U power. Okay, U or E square, whatever you call it, E square or U. For the time being, you take it as U as power. Okay. B naught cos squared theta. Okay. This is the power pattern. This pattern is given to you. Now, how do you find direction of maxima? Is same. You make cos squared theta is equal to 1, theta max, cos squared theta max is equal to 1. So you find the direction of maxima. How do you find the direction of null? You make cos squared theta n is equal to 0 and find theta n. Are you getting it? Direction of maxima, cos squared theta as cos squared theta max is equal to 1. You find the maximum. Direction of null, cos squared theta n is equal to 0. You find theta n null. Then half power point. How do you find half power point? How do you find cos half power point?
Equated to 0.707.
No. Cos squared
Cos
theta
squared
is
theta. Sir,
cos squared theta is equal to 0.5. You have to equate it to 0.5 because why? It is power pattern.
So U represents power.
I told you, no, E square or power. I just told you for the. I said if power is, if instead of electric field pattern, amplitude pattern, you have a power pattern. Power is, U is given as B naught cos squared theta. Then in that case, half power point, how do you find out? Cos squared theta is equal to 0.5. Okay, then you find out what is theta ht, and half power beam width. So in this case, you should not make the mistake of substituting cos squared theta hp is equal to 0.707. Only when amplitude pattern is given, you can substitute 0.707. Power pattern is given, which should be equal to 0.5. Okay.
Yes, sir.
So normalized, again, normalized power pattern, you know. How do you get normalized power pattern? Power pattern divided by the maximum value of maximum value. For example, B naught cos squared theta by B naught. B naught is the maximum value. So is cos squared theta. That is called the normalized pattern. So normalized pattern, everything is normalized. The maximum value is set equal to 1. Maximum value By changing the maximum value, the shape of the pattern does not change. The shape of the pattern remains as it is. It is only a scaling factor. Scaling factor. Okay. But many times it is convenient to use the normalized pattern compared to the normal pattern. Okay. Shape of the pattern does not change with normalization. Is that clear? Those points?
Yes, sir.
Okay. And procedure for finding maximum and null is also same. Maximum is equal to B naught you make, and minimum is equal to 0. Find n and m. Theta max and theta null. Okay. Okay, I will erase this. I will go to the next line. So you can make out how, and phi is equal to constant, how varying theta it will be a vertical plane. That is very important to know. If you keep phi constant and vary theta and from 0 to 2 pi, it will be the vertical plane. You can make out from this polar, this coordinate system, this diagram. If we keep phi constant, vary, that will be the vertical plane. And if you keep theta constant, vary 5 to 0 to 2 pi, it will be the horizontal plane. Okay, fine. So radiation pattern is mathematical and or graphical representation of radiation properties of an antenna, such as the amplitude, the phase, polarization, etc., as a function of angular space coordinates. Here's not included every property. There are power flux density, then radiation intensity, not just amplitude. This power flux density, radiation intensity as a plot of theta and phi. Okay. So few things which are very important. Pattern does not vary with R in R field region. It is a function of theta and phi only. Okay. That we will see later how it is like that. Amplitude radiation, a plot of field, electric field or magnetic on a linear scale field pattern. Power pattern, a plot of power proportional to either the electric square or magnetic field space on a linear or decibel scale. Okay. So when it is electric field, you use 20 log, and when it is power, this thing you use 10 log the power. You know that formula. Okay. So this is a typical pattern. A 2D normalized field pattern, EN, just said EN, normalized pattern. So you can see here. See here, this is EN, maximum value is 1. Okay, so here shown the half power beamwidth, because here said it is EN. Half power points are 0.707 on either side of the maximum. Okay. So after this becomes plus, electric field changes from plus to minus, minus to plus, plus, again minus, plus, minus, like that, minus, plus. See, for example, sin theta becomes plus, minus, like that. Similarly here, but since we plot the magnitude, it is of no matter. We plot the magnitude. So plus, minus, plus, minus, plus, minus. So these are called the side lobes. This is the back lobe.
Sir, I did not understand what plus minus is.
Okay, see, sin theta if you plot. Okay, so it is first plus, then it comes to 0, then it has to go to minus, no? Minus, then again it has to become 0, then plus, then minus, like that. So plus maximum becomes 0, then minus maximum, then again 0, then plus maximum, then again 0, then goes to in the minus maximum, again 0. plus maximum, minus, like that. So you will not be able to appreciate it unless you know the pattern, the expression for this pattern. Okay, what we plot is the magnitude. What we plot, we don't have to, even if it is minus, we plot because you can only plot magnitude here in this plot. Okay, this is the amplitude and angle. At different angles, you plot the amplitude. Are you able to? Do you know how to plot this plot? The pattern is not given to you, but the pattern is drawn. So what it is actually, or plot of amplitude versus angle. So these are the different angles: 0 degrees, like this, 90 degrees, 180 degrees, like that. Are you able to understand this?
Yes, sir.
Okay, when plus becomes 0, naturally electric field has to go to minus. Electric field is not just positive or negative. It is both positive and at some point positive, then it becomes negative, then again positive, then again negative, like that. So similarly here, it's positive, goes to 0, then it has to be minus. But we plot the magnitude part. We can't draw minus electric field in this plot. We can only plot the magnitude. Magnitude versus angle. Okay, so plus minus, plus minus, plus minus. So do you get it?
Yes, sir.
So half HPBW here. So this is the direction of maxima, 1. Amplitude is 1. Direction of maximum amplitude is 1. So half power beamwidth. So this is the half power beam. So there are nulls. There are many nulls here. First null, second null, third null, fourth null, fifth null, like that. There are many nulls. Minor lobe maxima. This is one minor lobe maxima. This is another minor lobe maxima. Another minor lobe maxima. Like that. Sorry, nulls. I didn't say. I thought I said my first null. Nulls there are many. First null is this. There are so many nulls here. Null one. This is the first null. This is the next. Okay. So wherever the pattern becomes 0, the value of the expression becomes 0, or yeah, that you get a null. Do you understand? Hello? Hello?
Yes, sir.
Sir, why are the minor lobes smaller in size?
Because the amplitude is less. Minor lobes is called because its amplitude is less than the major lobe. See, this is the direction of maximum radiation. The antenna radiates most of its power in the direction of main lobe. It can maximum power in the direction of main lobe. So in this direction,
Yes, sir.
okay. Any questions on this pattern? This is an example. He has just shown a pattern. Any questions? So can I go to the next slide?
Yes, sir.
Okay. Now this is a normalized power pattern, En square. You see magnitude of En square, normalized power pattern. Okay. So here the half power beamwidth will be 0.5. See half power between 0.5 between these 2.5 between these 2.5 half power beamwidth, because it is a power pattern, normalized power pattern. Maximum value 1 and half 0.707 into 0.707 is half. So you get this. This is the half power beamwidth, and these are the minor lobes. These lobes are the minor lobes. Just 2 minutes break. I'll just give 2 minutes break. Don't go away from your seat. Just keep looking at what I taught you till now. So all of you are comfortable till now? All of you are comfortable till now? You're okay?
Yes, sir.
Yes, sir.
Okay. Next, I'll go to the next slide. Okay, this is another pattern we have shown. Now, if you plot in decibels, the half power point will be minus 3 dB, minus 3 dB down. Because why? The maximum, if you call it as 0 dB, in a normalized pattern, what is maximum? 1. Log of 1 is 0, no? So 0 is the maximum point. So 0, this is the normalized power pattern. 0 is the maximum point. Half power point is minus 3 dB. Minus 3 dB. 10 log half. 10 log half. Okay. If it is a voltage pattern, again it is 0 dB, 20 log of 0.707. Okay. Are you getting it? Hello?
Yes,
Yes,
sir.
sir.
So I'll go to the next slide. This is an example, that's all. He has just shown what is half power beamwidth here. He has not given the pattern, the equation. Okay, he has just drawn the pattern. Polar pattern. Now he has given different things here. Personal beamwidth, major lobe, half power beamwidth, minor lobe, side lobe, back lobe, minor lobes, and all those things. So let me just explain one by one. I'll just explain. If you want, you can note down. Now, what is a major lobe? Major lobe is defined as the radiation lobe containing the direction of maximum radiation. Containing the direction of maximum. This is the direction of maximum radiation. Major lobe is defined as radiation lobe. Radiation lobe containing the direction of maximum radiation. A minor that is containing the minor lobe. A minor lobe is any lobe other than major lobe. So all these are minor lobes. A minor lobe is any lobe other than the major lobe. Minor lobe is any lobe other than the major lobe. So all of you getting what is major lobe and minor lobe?
Yes, sir.
I just get feedback only from 1 or 2 people. So I don't know whether the entire class is following or not. Please let me know, please. Otherwise, I will not come to know. Now, next, side lobe. What is side lobe? Side lobe is a radiation lobe in any direction other than the intended lobe. Side lobe, usually largest of the minor lobe. Largest of the minor, these are the minor lobe. So this is the side lobe, largest of the minor lobe. Okay, back lobe. It is the radiation lobe whose axis makes an angle 180 degrees with respect to major beam of the antenna. It is the radiation lobe. For example, here this is the back lobe. It is a radiation lobe whose axis makes an angle of 180 degrees with respect to the major beam of the antenna. Major beam of the antenna. Okay. So half power beam width. Half power beam width. What is half power beam width? It is the angle where P rate is less than half the P max. Radiated power is less than or equal to It is the it is between that range where the radiation power is P rate is greater than or equal to half the P max. So this here you have P max. So half, this is half the P max. So this is the half power beamwidth where P rate, radiated power, is greater than or equal to half P max. So are you getting it? It is the angle between half power points of the main lobe. It is the angle between half power points of the main lobe. This is the main lobe, major lobe or main lobe. This is the angle between half the power points of the main lobe. Have you got it?
Yes, sir.
For ideal directional antenna, there is no side lobe. So ideal directional antenna. Directional means it tends, it intends to, it is should send all the power in one particular direction. Ideal directional antenna should send power only in one particular. So it should not have side lobes. Ideal directional antenna should not have any side lobe. Okay, any questions on this pattern? It's called polar pattern. So angle versus amplitude. So again here you can see plus minus plus minus plus minus. I told you why it is called, why it is written plus minus plus minus. Okay, because no other way you can show it is minus. Is it clear?
Yes, sir.
Yes, sir.
Okay, now this is the linear pattern. Now here shown radiation intensity. Here's now radiation intensity is somewhere related to power. Power per unit solid angle, it is called. Power per unit solid angle. Radiation intensity. So this what you get is a power pattern. 0 degrees C, you can see here 0 to pi, 0 to pi, 0 to pi, 0 to pi. And this is a linear pattern. You can see here half power beam width, first null beam width, side lobe, back lobe, major lobe, minor lobes. So you may be asked to draw a typical radiation pattern, explain the different parameters. This is a usual question that is being asked. Draw a typical radiation pattern, explain the different parameters. So you have to show what is major lobe, minor lobe, first null beam width, SPBW, back lobe, side lobe, minor lobes, all those things. Okay, is it clear? Hello.
Yes, sir.
Now, what is radiation pattern? Can anybody tell me now? What is radiation pattern? In brief, can somebody tell me what is radiation pattern?
Sir, a graph between angle and amplitude.
It could be a radiation, any parameter. There are radiation properties, lot of radiation properties of an antenna as a function of angle.
Yes, sir.
Okay. So I'll go to the next slide. Okay. Normalized 3D pattern. How if you both vary theta and phi, how the pattern will look like? 3D pattern. See, this is the example. 3D pattern. Can you make out the difference between the 2D pattern and 3D pattern? Can you visualize the difference between 3D pattern and 2D pattern?
Yes, sir.
Okay. 2D pattern is basically cross section. You take it in some planes, cross section. You take in cross section. Okay. In the horizontal cross section, vertical cross section, like that. Okay. Now, what is electric field? Electric field, since we are dealing with polar spherical coordinates, it can have ER component, theta component, E phi component. So the overall electric field is ER square, E theta square, and E phi square under root. Have you got it? Hello? Electric
Yes.
field. So electric field is where usually ER component, you will see that in far fields, ER component will be 0 or very negligible. We'll study about that in detail. ER component will be almost 0. Okay. You have only transverse component, E theta and E5 components in the far field. These things you have to remember because it's very important. Like, you will see that it is important, very important. So we'll skip that. These are not required. Field pattern, linear scale, power pattern. No, this okay. Amplitude radiation pattern. Amplitude radiation pattern means plotting of amplitude with respect to angle. Theta and phi. So when we plot, we can make three classifications. An isotropic source, a directional pattern, and omnidirectional pattern. Okay. Now, what is an isotropic source? Have you heard about isotropic source?
Sir, idle antenna which radiates in all directions.
It radiates power equally in all directions. It radiates power uniformly or equally in all directions. Okay. Okay. Is it okay? Isotropic radiator it radiates power uniformly or equally in all directions. Have you understood this? Hello, isotropic source. Hello.
Yes, sir.
Now, can you tell me what is the pattern of this isotropic source? What is pattern? Pattern is you draw the pattern as a function amplitude as a function of theta, amplitude or power. So, what is the pattern? How the pattern of isotropic source will look like? How the pattern?
Sir, it will be spherical.
It will be spherical. When you plot it in two planes, when you plot it in theta is equal to constant plane or phi is equal to constant plane, what do you get? When you plot it in theta is equal to constant plane is what? Theta is equal to constant plane is horizontal plane. Theta is equal to constant plane. Are you able to be all of you visualize that? Theta is equal to constant plane is a horizontal plane. When I explained the coordinate system, I told you how it is horizontal plane. So, what is the pattern of isotropic source in theta is equal to constant plane?
It will be a circle.
Yeah, in both the planes, in theta is equal to constant plane and phi is equal to constant plane, you have circle or an isotropic source, pattern as a circle. Are you getting it?
Yes, sir.
Okay. Now, okay. Now, what is a directional antenna? Now, the example, last example, what I showed you, was it what type of antenna it was? Pattern was what type of pattern it was? Isotropic, directional, or omnidirectional? It was directional. What is a directional antenna? A directional antenna is one which has the property of radiating or receiving EMW more efficiently in some directions than in others. A directional antenna is one which has property of radiating or receiving electromagnetic waves more effectively in some direction than in others. Radiating or receiving more in some radiating or receiving more effectively. That means more focused in one direction. Most of the power is sent in that direction. So that is the directional antenna. You get it? It is not like a broadcast antenna, where it is supposed to be like omnidirectional. Sorry, isotropic. Directional antenna, okay, is not like isotropic. It is Directional. It's pointed in one direction. Got it? What I'm saying? The examples, the recent examples, what we saw were all directional antennas. Do you get it?
Yes, sir.
Ideal directional antenna should have no minor lobes at all. Ideal directional antenna, it should be only one main lobe. Now, what is the omnidirectional antenna? So, isotropic we have seen, isotropic pattern we have seen, directional pattern we have seen. What is the omnidirectional pattern? Now, omnidirectional pattern, I'll tell you, for example, suppose E is equal to B naught sin theta. E is equal to B naught sin theta, like this. Okay. E is equal to B naught sin theta. Now, this is called an omnidirectional pattern. Because why? In the phi is equal to constant, if you plot this, it is not function of phi. Okay. E is equal to B naught sin theta. It's not a function of phi.
Excuse me, sir.
If you, yeah.
So your voice is not clear.
Voice is not clear. So, have you understood isotropic and directional antenna?
Yes, sir.
Okay, you could make a difference. Make out the difference between isotropic and directional. Now, omnidirectional antenna, I'll tell you. It is in between isotropic and directional. How will you see? For example, if you have electric field pattern as B naught sin theta, for example, we have plotted this B is equal to B naught sin theta. We plot it in two planes. One is phi is equal. This B naught sin theta is not a function of phi. B naught sin theta is not a function of phi. If you plot this in phi is equal to constant plane, what you will get? You will get a pattern like this. Phi is equal to constant plane. You will get a pattern. E is equal to B naught sin theta. If you plot it, or in the phi is equal to constant plane, that means you vary theta from 0 to pi. You get a pattern like this. Do you understand?
Yes, sir.
In the theta is equal to constant plane, what is the pattern? In the theta is equal to constant plane, what is the pattern for this B naught sin theta? In the theta is equal to constant plane. This is phi is equal to constant. Phi is equal to constant. Constant. In the theta is equal to constant. What is the pattern? Theta is equal to constant. What is how the pattern will look like? In the theta is equal to constant, how the pattern will look like? Hello, are you able to hear me? Hello?
Yes, sir.
In the theta is equal to constant pattern, how the pattern will look like? E is equal to B naught sin theta.
Sir, your voice, sir, we can't understand you, sir, what are you saying, sir?
Since when your omnidirectional, I am just explaining what is an omnidirectional pattern. Okay, I am just explaining omnidirectional pattern. I took electric field E as B naught sin theta. Okay, and I am drawing the radiation pattern of this E is equal to B naught sin theta. So in the phi is equal to constant plane, the pattern is sin theta in the phi. The phi is equal to constant plane. Pattern is sin theta like this. Right now? Hello? Hello?
Yes, sir. Yes, sir.
In the theta is equal to constant plane, how is the pattern? In the theta is equal to constant plane. what will be the pattern?
So B naught. So it's just a
So if you want to plot B naught, how the pattern will look like? It will be a circle, constant in all directions. Whatever phi you take, if you plot phi against phi, phi is equal to 0, phi is equal to 30 degree, 90 degree, it will be a circle. Okay. Hello, are you getting it?
yes sir, yes sir.
So omnidirectional pattern is like this. E is equal to B naught phi theta. On one plane it is a circle, and in the other one plane it is like isotropic. Other plane it is directional. In the other plane it is directional. In the other one plane it is isotropic. Have you got it? Very important.
Yes, sir.
So omnidirectional antenna is
Now,
isotropic in one direction and directional in other plane.
yes, in one plane it is like isotropic pattern. In the other plane it is like directional pattern. And B naught sin theta is an example of that. Have you got it? Have you got it? Hello?
Yes
Hello?
sir, yes.
Okay, now I'll erase what I have written. So you have understood what is isotropic source, what is directional pattern, what is isotropic pattern, directional pattern, omnidirectional pattern. Isotropic antenna, directional antenna, omnidirectional antenna. Omnidirectional antenna will send pattern like this. It need not be just sin theta, sin square theta also is omnidirectional. Okay, because on one plane you should get like a circle, and other plane you should get a directional beam, directional pattern. Okay, have you got it?
Yes sir.
So can I go to the next slide? Okay. Now this is a horn antenna. He is showing the H plane and E plane in this. He is shown the radiation pattern. The electric field lines. You have seen in a waveguide, electric field lines, how they are aligned, how what is their direction. See from here to here, in fact, it's like this parallel. And H fields are horizontal. E fields are field lines, electric field lines are vertical. E10 mode. Have you heard of it? So this is the pattern of the radiation pattern of the horn antenna. And he is explaining, instead of theta is equal to constant and phi is equal to constant plane, he is explaining E plane and H plane. Sometimes instead of theta is equal to constant plane and phi is equal to constant plane, they are using E plane and H plane. Now what is E plane? Plane containing electric field, and the direction of maximum. This is the direction of maximum radiation. Plane containing electric field and direction of maximum radiation. Basically, this vertical plane. And what is H plane? Plane containing the magnetic field, horizontal, and the direction of maximum radiation. Direction of maximum radiation. So instead of explaining sometimes theta is equal to constant plane and phi is equal to constant plane, they say E plane, H plane. So he has explained what is E plane and what is H plane. E plane is plane containing the electric field and direction of maximum radiation. And H plane is a plane containing the direction of magnetic field and direction of maximum radiation. Have you understood this?
Yes sir.
Sir, can you repeat it one more time?
Hello, yeah.
Can you
Yeah.
repeat what you just said, sir?
See, sometimes you don't speak in terms of theta is equal to constant plane and phi is equal to constant plane. We speak in terms of E plane and H plane. Now, what is E plane? E plane is plane containing the electric field and direction of maximum radiation. That is this vertical plane. Vertical plane. And what is H plane? Plane containing the direction of the magnetic field and direction of maximum radiation. Direction of maximum radiation here. X. Given X here. So this is horizontal plane is the H plane, vertical plane is the E plane. Have you got it?
Yes, sir.
Sometimes we don't speak in terms of theta is equal to constant plane and phi is equal to constant plane. We speak E plane or H plane like that. Now, what pattern is this? Can you tell me? Oh, it's already there in that slide.
Donut.
Omnidirectional pattern. Can you understand? Visualize. This is an omnidirectional pattern. Can you understand that this is an omnidirectional pattern? What is the pattern in the phi is equal to constant plane? What is the pattern in the phi is equal to constant plane?
Sinusoidal.
Huh? What is the pattern in the phi is equal to constant plane? It is like sine theta, what I showed you. Right? No? Something like sine theta. Can you understand this? Hello? Hello?
Yes, sir.
And in the theta is equal to constant plane, what is the pattern? It is a circle. In the theta is equal to constant plane, it is a circle. So this is an example of omnidirectional pattern. Have you got it? Like how do you plot sine theta? If you make a 3D plot of sine theta, how it will look like? Are you getting it? Hello?
Sir,
Yes,
sine
sir.
theta part is okay, but sir, can you give some brief about the circle part, sir? Not able
Circle.
to
See, if you keep the theta is equal to constant, you see it is a circle only, no? Theta is equal to constant. In the theta is equal to 1, you see it is on the top. So if suppose you close it fully, what do you get on the theta is equal to, it's a circle. Like isotropic source. Theta is equal to constant, you vary phi from 0 to 2 pi. With respect to phi, it doesn't vary. With respect to theta only it varies. With respect to phi, it doesn't vary.
yes, sir. Yes, sir.
So for example, B naught sin theta is like this. B naught sin theta almost. Are you getting it? Hello?
Yes, sir. Yes, sir.
Yes, sir.
So this is an example of omnidirectional. In one plane, you have isotropic pattern. Other plane it is a directional pattern. Okay.
Yes.
Okay. Shall we continue? What is the time on this? Okay. Shall we continue tomorrow? Hello.
Yes.
Yes, sir.
So what is radiation patterns? Where do we see it? In the far field region. The far field, far away point. It is a pattern is not in the near field region. It's a far away point, and the pattern is independent of R. What R pattern shape is independent of R, and at R point, the ER component, far away field ER component will be 0 usually, or very insignificant. E theta and the electric field lines will be transverse. Direction of propagation of the power is in the R direction. direction of the power is in the R direction. So to completely enclose the antenna, we have to vary theta from 0 to 2 pi and to 5 to 0 to 2 pi. So if you want to find the power radiated by the antenna, you have to power density E square, and you have to integrate it. You have to multiply by the area and integrate from theta limits to theta is equal to 0 to pi and pi is equal to 0 to 2 pi. When you completely enclose the antenna, you can capture the total power radiated by the antenna. When you totally complete sphere, completely enclosing the antenna and varying theta from 0 to pi and pi to 0 to 2 pi, you can capture all the power in the antenna radiated by the antenna. Okay? Hello?
Yes, sir. Got it.
No. Okay. So we'll continue tomorrow. I will just set the class in the evening. That your tomorrow's class is not. I am not this thing. Set the class by evening. I set it, and you will get the link, or you will be able to join tomorrow 9:30. Is it clear? Hello?
Yes, sir.
Okay, we will wind up then. It's fine today. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Hello, attendance, can I take attendance? Attendance. Hello?
Yes, sir.
Yes, sir.
Attendance.
Yes, sir.
Sir, most of the guys have left, sir. It is 1:40 right now.
No, they are not supposed to leave, no. Okay. Okay. Fine.